In this video, I'm going to be going through the 2003 trial, but only focusing on the mechanics questions, and this will provide a good practice exam for the mid-course review for HSC or Year 12 Engineering Studies. So to start off with, I have a E equals flea, or a Young's modulus, or a strain, or an elasticity question, and I'll just go straight to my working out. So what I've done is I've taken the information from the question and I've provided in what I call a data set. So this here is data. Okay, so what we've got is the original length is 5,000 millimeters. The mass is 118 kilograms. The diameter is 3 millimeters. The change in length, or the elasticity, is 4 millimeters. We haven't been given the stress. We haven't been given the strain, but we know the formula for stress is force over area. We haven't been given the strain, but we know the formula for strain is either extension over length or change in length divided by original length. The formula for Young's modulus of elasticity is either stress over strain or FL over EA. We haven't been given that, we have to calculate that. So the first thing I've done is I've said, well, F equals mg divided by, F equals mg. So I'm just using the value of 10 for gravity. So we're going from 118 to 1,180 newtons. Then I'm going to find the area. So I always use the formula pi d squared on 4. I was just asked about this, and I'm just going to highlight that this is the same as saying pi r squared, but it's more useful for engineers because we're always going to be given diameters. We're never going to be given radiuses. We're going to use pipes, and we're going to use bars and rods, but we're never going to use radiuses for these sorts of equations. So when we substitute the value of the diameter into the diameter, we get 7 millimeters squared and some change. And when we take our force that we calculated here divided by our area, we're going to get that value for stress. For strain, now in the answers, I'm going to point out that I made a mistake, but I do have written answers for this test, and those answers, they said 3 for some reason. That's incorrect. The answer is 4, and that gives us a strain of 0.0008, or 8 times 10 to the negative 3. A student has pointed out that I used the wrong value. I dropped a 0 for my strain in the calculation, which meant that my numbers were up by an order of magnitude of 10. The important thing to remember here is 2 things, is that estimation and having a rough idea that a Young's modulus of elasticity for steel is often in the 210 gigapascal range helps. Also, knowing that you probably wouldn't lose a mark in the HSC for that because that's a clerical error. You've provided the correct answer directly above. I'll let you the correct answer for strain. They can see that you've just substituted the wrong value, especially if it's something as clear as a missing digit or missing 0. So we're going to do the Young's modulus calculation. We're going to say Young's modulus of elasticity is equal to stress divided by strain. We've already calculated the stress as 166.9 megapascals, and we've already calculated the strain as 0.00, so 308, and that's why I did wrong there, 0.0008. Now that strain, we've made that calculation by using millimeters, and our stress is in megapascals, so that means our answer is going to continue to be in megapascals, and we're going to get 208 point something megapascals, which rounds up to 209 gigapascals. So the next question is a truss, and it's got a lot of forces, which makes it look a bit more intimidating, and it definitely I think can increase the chances of making a silly mistake. But what we're going to do is, first thing I'm going to do is, we don't need that anymore, we can put that over there. We need to find the reaction. So the reaction, we should be pretty comfortable with finding reactions at this point. So we're taking moments about L to find R. Now a smarter student might actually take moments about R to find L. You're totally allowed to do that, and that would be because we really want to find L anyway. But I've used this equation to find R. And what I've got is 8 times 1. You'll notice here that something worth mentioning is that I have replace the value. I don't really care what the distance is between these because they're all equal, and that's why I've replaced those numbers with 1, 2, 3, and 4, is because it makes my maths a lot easier, and when I can calculate that faster, it's easier for me to get that answer. I was sort of rushing through this. So the next thing we're going to do is we're going to find the reaction. I notice it's a different color because I notice that my reactions weren't even close to being equal, and that's something worth considering. Is it if you have reactions where one is 26 and the other is 120, doesn't mean it's wrong, but you really want to think about, okay, just check some of the forces again, just make sure. And a thing you can do is I know I haven't really taught this a lot, but something you can do is if you can take moments about L to find R, and you can take moments about R to find L, you actually have a third way, you have three ways of finding, you have a duplication in our answers, which means that you can check your answers yourself. If you have time, it's worth taking moments from the opposite side and just checking that you got the same value. And that's a way of checking your work. Okay, so what we've got now is to find A, I've taken this section of the truss. So I've taken this section of the truss here. I've put my cut through there. Now, showing your cut is fine. Also, redrawing your truss is fine. But when you redraw the truss, it's really, really critical that you don't forget extra forces like this one here, because forgetting a force is you're going to get the wrong answer. And I have forgotten forces more than once, including this 8 here. Okay, so first thing I've done is I've labeled all of the cut members. Whenever I don't have a name for a member, I call them P and Q. And in this case, P and Q don't meet, so I'm using the lone wolf. The lone wolf means that we're going to use the sum of the forces vertically or horizontally. Because A is the only one that has a vertical component, well, A is going to be the lone wolf in this case, and it's going to be the sum of the forces vertically. Now, we're assuming tension, so we're assuming this force is going to go down. We don't have any reason to believe it's tension, just that we always start with tension, and then that way if we know if we get a negative answer, that we've done something wrong. So what we've said is, well, we need to have 25 going up, 8 going down. How much more down will we need to balance that out? Well, we'll need to have 17 down. We assume down, so therefore it's positive, therefore it means our tension is correct, that our assumption is correct, that it is in fact tension. Okay, so then we know that this value that we just calculated is the vertical component of A, which is 17.3 kilonewtons. So the total of A, using the trigonometry of this little triangle here, is going to be AV divided by sine 30, divided by sine 60. AV divided by sine 60 is 17.3 divided by the disco number, which gives us close enough to 20. And we've already determined it's in tension, but I should write that just to make sure. Absolutely sure that we've got that. Okay, so we've now done our truss, and we can move to next question. Okay, we've now got a cable railway taking tourists at the top of a mountain. It's 18 tons, 30 degrees, velocity of 5.4, coefficient of friction of this, and an efficiency of that. So if we have a look at our question, this is what it looks like. Now, because it's moving, that means friction is going to increase the tension on the cable, right? If it's moving, it's going to increase the tension on the cable. If it wasn't moving, if we were just trying to hold it stationary, then in that case, friction will actually reduce the amount of tension on the cable. So in this case, the component of gravity, what we call the WX, or more accurately mg sine theta, because I don't like to use W's for weight, but I wrote it there just because otherwise it's a big long formula. The component of weight is going to add to friction. It's not going to be subtracted by friction. So in this case, they've told us that the weight of the mass of the train is 18 tons. So our weight is mg is going to be 180,000 newtons. Now, again, it's easy to be sloppy and lose a zero there. I think that as long as you've written it correctly somewhere, for instance, if you just wrote 18 here, as a teacher may or may not have done, generally teachers are pretty good with carried errors. They understand that you're under exam conditions, and my experience with talking to a lot of teachers who have experienced HSC markers, and my own personal experience, is that we are not going to deduct marks for clerical errors, for dropping a 0. As long as you've demonstrated that you understand that you had to multiply by 10 somewhere, we're not going to take away that mark because you've done something wrong. But it is critical that you must show working out. In the current HSC guidelines, if you just put down an answer, it doesn't matter if it's correct, you will not get any marks. Okay, so I've drawn this diagram. I've put the coefficient of friction, I've put the velocity. I've converted that velocity into meters per second, and I've got my efficiency of 75. Now, I like this too many guys formula, right? That for me is an easy formula for me to remember and easy for me to write down. And then I expand it, and that helps me remember that this is the component of weight, and this is the force due to friction. And so I've just entered the values there. I've plugged those values in. This is the part, if you want to get something wrong, this is the part to get wrong, is the part they put through the calculator. And that gives me this answer. This answer is the force that when we do power, we say power equals force times velocity. And that power equals force times velocity. In this case, the force is this tension. This tension is a tensile force. So what we're going to do to calculate the power, so the formula for power is fight the power FV. That's on the formula sheet these days. Once upon a time, power was just written as work divided by time, but we can manipulate that that formula if we make it a Fs divided by T. S divided by T is velocity, and we can get fight the power FV. So power equals force times velocity. The force is 136,000 multiplied by velocity of 1.5 meters per second gives us this answer here. And the unit for power is watts. Then we're going to say efficiency. Efficiency is equal to power out divided by power in. We can never get more out than we put in. So if we're saying that is equal to 75, we can rearrange that formula, and what we can do is we can say that power in equals power out divided by efficiency. Power out equals that number divided by 0.75, which means the amount of power that we're putting into the machine is going to increase. We have to have more energy coming from the machine than we have to put more money into the machine than we get out of it, because we're going to have losses due to friction. Okay, so that question is done, and we can now move on to this one. Again, the written answers, I think that I don't have the official written answers, I only have a teacher's written answers, and I think this is a difficult question because this is a question in effectively 3D space. The weight of the car is given as, well, they've told us the mass of the car is 1 ton, which is that ton is divided in the front and back, but they've said calculate the maximum bending stress on each beam. Now that means that assuming that this car has its weight evenly distributed, which we have to do, there's no other way that we could interpret this question, that means that we're going to have half of this mass on each reaction. So we've got reactions of 450 and 550. We actually halve those as far as I'm concerned in order to, so we're going to multiply them by gravity, and then we're going to divide them by 2. So that we're going to effectively multiply them by 5 to get these two reactions. When we get those two reactions, we can then get a bending moment diagram, and then from the bending, well, a shear force diagram, then we'll get a bending moment diagram, and from the bending moment diagram, we will be able to calculate the bending. So what we've got is 450 times 10 divided by 2, right? 450 times 5 is this number. Sorry, that's not true. That's not true. It's this number, 2250. So what we're going to do is we're going to calculate our reactions, which you can see I've calculated the reactions here. And I've got L and R. And once we've got L and R, we can then draw a shear force diagram, which I show looking like that. And we can reasonably assume that wherever we cross the x-axis is where our maximum bending moment is going to occur. Our maximums or minimums, right? Our turning points, if you do calculus. And so, in this case, to calculate the maximum bending moment, the easy way of doing this is just to calculate this stress block here. So we've got 2 meters times 2467. And that gives us this number. That's our maximum bending moment. Now, I will tell you that the answers that I have, they had twice that number, but that's because they didn't halve the force on each side of on each beam. And I'm pretty confident that that should be that's what you're supposed to do. So then we have bending stress equals my over I. M is maximum bending moment, I is the distance from the neutral axis to the extreme fiber, and I is the second moment of area, also known as the section modulus. Sorry, not section modulus. The moment of inertia. Okay, so the I will always be provided, or it will be the thing that we're calculating. Y is equal to, because this I-beam is shown as a rectangular section, right? It's a rectangular section of 200. Our Y value is going to be half of that because it's a symmetrical rectangular. Sorry, it's not a rectangular section. Because it's a symmetrical section, we can say that Y is half of 200, and the I value is, as we can see there, given. IXX is, funnily enough, given this orientation, it is an IXX, though that would be, in fact, the IYY that you would look up in the book, but I don't want to confuse you, so we're just going to know that it's the second moment of area. So if you look these values up in the book, they will give you an IXX and an IYY. This is not the way that beams would normally be rotated. They would normally be standing so that they look like an I and not an H. And by putting it as an H, we're going to get a much lower second moment of area. And we identify that by giving them two different second moments of area, or two different moments of inertia, the IXX and the IYY. The IXX is the larger of the two, so I think it's actually confusing here. I think it's inappropriate for them to have written IXX, but we're not going to worry about that. We're just going to move on. I've just written I as our value. So we've got my over I, so we've got M, which is our maximum bending moment. Now, in this case, the answer is already in Newton meters, which is great. And our I value is already in meters, which I hate, and that's not the industry standard, but in this case, it works out well because we're using the same values. We're using meters and meters. If we use meters, it means our answers are going to be in pascals. And we always use newtons. So if this had been, we're just going to keep on going there. Okay, so we're going to get 4,900 and something multiplied by, now we need to convert the Y value, the Y bar, the distance from neutral axis to the extreme fiber. We need to convert 100 millimeters. It should actually say millimeters there. I'm too lazy to change it now, but 100 millimeters is the same as 0.1 meters. So what we've got is 4,900 times 0.1 divided by the given value of 2.2 times 10 to the negative 4. Put that into a calculator, we get a number that's in the millions, 2.3 million something, which we're going to call 2.3 megapascals. And we've got one more question. Okay, the last question is, two pins support a ramp at B. The pins are in double shear. There's a factor of safety of 5. The maximum allowable stress is 450. You'll notice it's yield stress, right? For bolts, we use yield stress. When we punch a hole through steel, we use the UTS. So the UTS is typically the value because when we punch a hole, it doesn't matter that it's failed. It doesn't matter that it's yielded, right? It doesn't matter that it's given up. What matters is that you need to go all the way through. You need to punch a hole clear through. So if they give you two values, you have to use the yield stress and not the yield stress for bolts and the UTS for punching a hole. Calculate the diameter of the two pins, assuming them to be in double shear. Okay, so if we go to this question, we've said two pins in double shear means that our total area is going to be equal to the area of the bolt multiplied by 4. We've got two bolts and they're being cut twice, which means we're going to have four diameters worth of four circular cross sections being cut. Our maximum load is 7 tons, which we're going to convert into newtons as 70,000 newtons. Where our yield stress is 400 MPa. Our factor of safety is 5. So we know that stress equals force over area. Area, we can rewrite that formula and say area equals force divided by stress. You can use the triangles to calculate that, or algebra. I think that the triangles have a place, but eventually algebra just becomes easier and faster. So what we're saying here is we've got 4 times the area equals 5 times the force divided by stress. Now, again, you can see this has been, I've rewritten this because I'd had a pretty big day when I wrote this. I'd actually had a fairly big, I'm not going to go into that. Anyway, but the point is that we've got exam method. People make mistakes. We don't expect people to be perfect. As long as they've shown good reasoning, there's a lot of room for marking, and we just want to. But remember, in professional engineering, we have a verification process. People are supposed to be checking, and they're supposed to be verifying that you've done your correct calculation, so that people don't die. Okay, so what we're saying is 4 times the area equals 5 times this force of 70,000 newtons divided by 450. So we get 4 times the area equals 777.7 repeater. That means the area of each bolt is going to be 194 millimeters squared each. Now again, we're going to say that area equals pi d squared on 4. If you want to use pi r squared, that's fine. You're allowed to do that. But eventually, professional engineers all come to the conclusion that it is faster to do this. And then it's also, a really handy trick to remember is that diameter equals the square root of 4 over pi. Now, you don't need to remember that. You can use your algebra, and I will be honest that I recreate this every time out of algebra. But if you can memorize that formula, it would probably save you some time. Okay, so we're going to substitute those values. So this 4 times 194, which is just this number here that we already had, divided by pi, take the square root of everything, we're going to get 15.7. 15.7 millimeters. Well, you can't buy a bolt that's 15.7 millimeters, so instead you can use the 16 millimeter bolt. In practice, you probably would actually get away with a 15 millimeter bolt, but we're not going to worry about that. That is the answers for the parts of this test that relate to mechanics. Good luck in your assessment task.